Hello there. It's time to do a bicycle problem. This one, we're dealing with Nisha, and her bicycle has a crankset with diameter 6 inches, rear sprocket diameter 1.5 inches, and rear tire diameter 3 inches. So step one, let's get a picture of what's going on here. So back here we're going to have the rear sprocket, and that attaches via a chain to the crankset, which we know is 6 inches in diameter. And the rear sprocket is attached via an axle to the rear wheel. And the wheel has a diameter of 30 inches. Okay, so that's our sketch. And we're going to pedal here. That's going to feed the chain. So this is going to be moving. That movement's going to turn the rear sprocket, and the rear sprocket turns the axle, which in effect will turn that rear wheel. So we're going to write a rule relating the angular velocity, that's the speed that this is rotating, the angular velocity of the rear sprocket, so the speed that that's rotating, to the angular velocity of the crankset. Okay, so we're going to write a rule to find this speed based on this speed, because that's going to be our input. Now there's this whole long thing here about how the linear velocity is equal to the circumference times the angular velocity, and the linear velocity of the crankset is equal to the linear velocity of the rear sprocket. That chain needs to be moving at the same rate here around the crankset as it is here around the rear sprocket. And in class we set those two things equal to each other and divided through and got a rule based on their angular velocities. Now the trick here to shorten this all up is the angular velocity of the rear sprocket is based on the angular velocity of the crankset, with a ratio of their radii or their diameters. Now the trick for remembering which way to do that ratio is this one is bigger, so this one's going to rotate faster. So that's going to be 6 over 1.5 then. Dividing through, that's going to give me 4, so this is going to spin 4 times faster than this one. If you reverse it, you would get that this is spinning 4 times slower, which shouldn't be the case. Okay, so that's going to be our rule for that. Now we know that she's pedaling at 70 miles per hour. Okay. Looking for her speed in miles per hour, ultimately we're interested in the linear velocity of that rear wheel. So a little bit of labeling here. She's pedaling at a speed. This crankset, that's going to rotate at 70 RPMs. That feeds into that rear sprocket, which then feeds into the rear wheel. Okay, so one question is, well, how fast is that rear sprocket rotating? Alright, we'll multiply through here. So that's how fast the rear sprocket's rotating, 280 RPMs, and that is also how fast the rear wheel is rotating, because the wheel is attached to the sprocket via an axle there. So if that spins at 280, this whole thing here spins at 280. That is much bigger, that's why you go faster. So we want the linear velocity of the wheel now. And the linear velocity of the wheel is equal to the circumference of the wheel times the angular velocity of the wheel. So what's circumference? 2 pi r. Actually, we're given the diameter, so it is diameter 30, which is in inches, times pi, times the angular velocity of the wheel, which is 280 rotations per minute. Now if you're thinking dimensional analysis here, that 30 pi inches, that's actually equal to 1 rotation. So what you'll see here is when we we'll actually get those rotations to cancel out when we do our dimensional analysis. Actually, I suppose we could cancel them early here, that those rotations are going to cancel. And the units that when we multiply through here, we would wind up with inches per minute. But we don't want it in inches per minute, we want it in miles per hour. So we're going to have to do a longer dimensional analysis. Alright, so those rotations are going to cancel as we talked about. There are 60 minutes in 1 hour. And this is going to get me to the hours, so that's good. And then there are, so I have inches on top here, I'm going to have to put inches on the bottom. There are 12 inches in 1 foot, and there are 5,280 feet in 1 mile. So when I multiply through rotations, those cancel out, the inches cancel out, the minutes cancel out, the feet cancel out, and the units that we'll be left with is this one here and this one over here. So we'll be left with miles per hour. And then we just carry out all that multiplication. Okay, so this one gets pretty long. Let's round it. So her speed at the end is 25 miles per hour. Those will both get bumped up there. So these can be kind of long problems, but you want to have a strategy for them. You can really pay to draw the picture to get an idea of what's going on, where the things are that are rotating. You got to get these relationships right. It's the biggest thing here. So like this part right over here, knowing which way to set that up. And the trick, remember, is they're attached via a belt here. This one's smaller, so it has to spin faster. The bigger, it's got to spin slower. So that'll tell you which way to set up that ratio. And then for the rest of it, it's this rule in here, linear velocity is equal to the circumference times the angular velocity. You're going to want to label a lot of the parts here. I'm using a bunch of subscripts so that I can see, oh, okay, this was the angular velocity of the rear sprocket, this one. Here I'm doing the linear velocity of the wheel. And then you got this dimensional analysis to finish the rest of it out. All right, thanks for watching. Character and Scholarship for Life.